let's talk about how we can actually find our electric potential difference from our electric field. There's different ways we can find our electric potential. One of them is one that we've done and seen before, which is you can add up the electric potential due to all of your charges in your system. That's totally a thing you can do. But if you know something about your electric field already, you can integrate along a convenient path to find your electric potential difference. What I mean by that is this. So going back to thinking about your potential energy, the electric potential energy is equal to the negative of the work done by the electric force. And I can put in information about how I can calculate my work here as my integral from some initial position to a final position of my conservative force dotted over a path. And so we're going to use this definition of our potential energy to help us come up with an equation for our electric potential difference. So now what I'm going to do is remember that my electric potential difference is equal to my electric potential energy divided by a test charge. And now what I'm going to do is I'm going to take this expression and plug it right into that expression and simplify a little bit more. So what I've done here is I've taken my integral for my delta U and I've pushed in Q test into this integral. I can do that because Q test doesn't depend on R. It's just a scalar. And now I can identify as F over Q as my electric field. So through this method here of working from my definition of my conservative force and my electric work done on a system, I can think about my electric potential as the integral, the negative integral from some initial position to a final position of my electric field dotted over this path. So let's actually see how this works in practice. We are going to think about a single point charge in order to calculate our electric potential difference. So let's first draw a quick picture. So let's imagine that I have a plus Q charge here, and I can think about my electric field. So my electric field starts with some big magnitude, and it will get smaller and smaller as you get farther away from your charge. And now let's say that I wanted to calculate my electric potential difference from some initial position, I'll call this Ri, to a final position somewhere over here that I will call Rf. So I want to calculate what is my potential difference starting here, and I'm thinking about moving along this electric field vector map here to go to this location here. Okay, so let's take our delta V here is equal to the negative of the integral of this initial position Ri to this final position Rf. And I'm going to plug in my expression for E here. So I've got kq over r squared r hat. And that's dotted with the path dr. And I'm moving from this position to this position in the positive r hat direction. So I'm going to write dr r hat. All right, so now I'm going to simplify this a little bit more, and I'm going to pull out some constants. I can pull out k and q, so I've got minus kq times my integral. My dot product goes away. R hat dotted with r hat gives me 1. So I'm left over from my initial position to my final position of 1 over r squared dr. Okay. Now I just need to finish the integral. So I get, this is my delta V, my change in electric potential is minus kq. And I know that my integral of 1 over r squared is minus 1 over r. And I'm evaluating this integral from r initial to r final. And right away, this is looking really familiar. This looks like the electric potential that we've already defined before, but instead we're getting it directly from our electric field equation. So I'm going to simplify this a little bit more just to finish this out. So I've got kq, the minus signs cancel, times 1 over r final minus 1 over r initial. Let's think about this for a quick second. I am, Rf is bigger than Ri, right? Rf is bigger than Ri, so this whole term here is going to be negative, right? I've got 1 over a big number minus 1 over a small number, so this one will end up being overall a smaller number, and this one will end up being overall a bigger number. So I've got a small number minus a bigger number. This should end up being less than 0. And this is making sense just based on what I already know about the electric potential for a single charge, that when I'm near a positive charge, I have more electric potential. So I should expect that if I were to take the difference between this electric potential and this electric potential, right? I'm going from initial to final. So if I wanted to, I could sort of label this as my initial potential and my final potential. So my delta V is V final minus V initial. This should be a smaller number compared to this V initial number just based on what we know already about the electric potential. So we already expected that this should be less than 0, which is what we see in our calculations. So this is one example of how you can use the electric field to find your electric potential difference between two locations.